So the electric field is going to be reduced, as we talked about here. So that gives us now some physical insight into what's going on at the microscopic level. All right. So now we have that idea in mind. Let's see if we can quantify it a little bit. I'm going to set up a sketch here and then talk through it. But in the interest of time, I also set up some of the relevant information before we started. It's on the left-hand chalkboard. So we're going to work our way through that. But before we do, let me just set this up here. Okay, so here we go. We're going to try and figure out about the electric fields and charges and so on and so forth. So dielectrics. We're going to analyze using Gauss's law, as we might have done in the past, to figure out the electric fields. And so here we go. So I'm going to start off with a schematic of my parallel plate capacitor, initially without a dielectric. The usual setup here. Then I'm going to throw the dielectric in. Let's make it pretty much fill the entire space. I'm going to talk about cases when it only partially fills the gap in a little while. So there's now my dielectric, and as we just talked about, I expect to induce charge with the opposite sign. Oops, that would help if I got this the right way around. I'm going to correct this in a moment. Let me just get rid of the pluses. So I've got minus on the right, on the capacitor, and so I have pluses on the right in the dielectric. Okay, so as we've described. Now I'm going to do my Gauss's law trick, as usual, which is to say something about, can I figure out the electric field in the middle? And remember what we were doing with Gauss's law with capacitors to find the electric fields. We were setting up a Gaussian surface that typically looks like this, okay? So remind you of the argument for doing this. First off, we want to find the electric field in between the plates. We expect it to be uniform. We're ignoring edge effects. So I'm going to draw this parallel and going up through the dielectric somewhere. I'm going to ignore edge effects, and we're bringing this side of the Gaussian surface down through inside the conductor, because we know the electric field there is 0. So this is my Gaussian surface. And what I expect with Gauss's law now is the following. So, a usual application of Gauss's law over a closed surface. And this now should be the net enclosed charge divided by epsilon 0. Okay, I need to label one last set of things on here, and I'm going to turn up to the board up there. This is Q in terms of the original charge on the capacitor plate, and then the induced charge I'm going to call Q induced. Okay, so that's the green charge of the opposite polarity on the face of the dielectric. Okay, so with all of that said, this then is presumably Q minus Q induced over epsilon. Let me just pause, make sure you're okay with this. So, red charge is the initial charge on the capacitor before I throw in the dielectric. I throw in the dielectric in green, I get the induced charge, Q in, on the external surfaces of the dielectric, and it has the opposite sign to the plate which it's butting up against. Okay, so let me take this and just quickly walk you through this. I want to get an expression for Q minus Q induced, which you see down at the bottom here. So hopefully this is the same sketch, the same color scheme. Let me pull this down a little bit. All right, so a couple of observations. Regardless of what type of dielectric I have, whether it's polar or non-polar, the turns out that the induced charge is proportional to the external electric field. Okay? So, useful empirical observation. So, fine. That's what we find regardless of the nature of the dielectric. Of course, the net electric field, as we already talked about, is going to be the superposition of the original electric field plus now the newly added induced electric field. We're going to have to worry about relative direction. Of course, these are vectors. Okay, so what are we going to make use of here? First off, a reminder, and this came from maybe a week or so ago, when we first looked at two charged parallel plates facing each other. We learned using Gauss's law that the electric field can be described simply as the charge density on one of the plates, Q over A. The plate here has area big A. So there's the charge density, Q over A. We learned that it's sigma over epsilon. And a reminder that the original factor of 2 that we had in the denominator applied to the case where we have a singly charged plate, not a pair of oppositely charged plates. And as you know, the electric field in the capacitor configuration with these facing oppositely charged plates gets doubled. So we know the electric field between these two charged plates is just the local charge density over in vacuum. All right. Now, we've also parameterized the electric field now with a dielectric in between as being the original electric field divided by the dielectric constant. That is maybe still on the chalkboard underneath here, so we know that. So I'm going to take this and say, okay, if I can say the electric field is this, and I know the electric field is just sigma over epsilon, and this becomes sigma over kappa times epsilon on the left side. On this side, I'm left with just the original electric field, sigma over epsilon 0. And here's the all-important minus sign reflecting the opposite direction of the electric field from the initial electric field, so minus the induced charge density over epsilon. And then I'm just going to clean this up, basically by removing epsilon to get to here, and then removing A just to get to the actual charges on the plates. Okay? So it's pretty straightforward, but I just want to make sure all the steps are clear. First thing is to note that the induced charge is proportional to the external E field. We've got to superpose electric fields. We can always describe the electric fields in the gaps between two oppositely charged plates by this relationship. Then I'm going to go back to this from here, make sure I throw in the minus sign, and what kicks out the bottom is that I can eventually say that Q minus Q induced is just the original Q over kappa. So that's what I was aiming for through these 5 lines of calculation. I want to replace Q minus Q induced over there somewhere by Q over kappa. So this now becomes Q over kappa epsilon 0. So we've almost got now a result that's somewhat useful. And so let me summarize what that looks like. It tells us that now what Gauss's law is going to look like. Basically, I end up with simply modifying epsilon 0 and throwing a kappa in front of it. Otherwise, it looks very familiar. You may occasionally see this written in a slightly different way. Let me just write it as follows. This reflects the possibility, which by and large we're going to ignore, that this is not constant everywhere within the material. If it was changing in some way, then I would need to fold this into the more detailed flux calculation. But I'm largely going to say you will not have to worry about that situation, that this is just fine. Okay? So, let's see, what do I want to do with this? We want to do some calculations, but before we do that, let me just pause and ask a
dielectrics
What do you mean?
wouldn't be really be dielectric.
I'm not quite sure how that could happen, because I require my capacitor plates to be conducting, and I require my dielectric to be insulated.
Oh, it has to be insulated.
It has to be insulated, yeah. Don't get confused by throwing something between the plates. It has to be insulated. There's no charge travel across the gap. Okay. I know that can be a little bit confusing, particularly when I tell you about putting water, for example, between the plates of a capacitor. All right. So, just one quick comment. Has to do with temperature dependence. This is just as an FYI, possibly for those of you who are going to be engineers, possibly of interest. Think about this underlying microscopic picture of these molecules orienting themselves preferentially in one direction, regardless of whether they're polar or non-polar. You know enough now from basic thermodynamics or kinetic theory to know what's going on when the temperature of a material increases. Given what you know, would you expect dielectric constants, these kappa parameters, would you expect them to increase or decrease or stay the same as I increase the temperature of my setup? Decrease. Why?
As the temperature increases, there's more likelihood of travel of charge to the material. Not as insulated.
Okay. I liked your answer, but maybe less so the argument behind it. Want to go? Temperature increases, resistance decreases, depends on the material. We don't even know really about resistance yet. Let's go to no.
Something to do with thermal expansion?
What's going on with the microscopic constituents as the temperature increases? Well, there you go.
Okay.
You want to make sure everyone saw that? Okay. So that's what's going on, right? As the temperature increases, we have more kinetic energy at the microscopic level. Our individual molecular constituents are moving randomly around at much higher speeds, so it's much harder to preferentially orient them in one direction.
Ah, okay.
So this thermal effect is quite strong with dielectrics. The capacitance actually more or less goes with some inverse temperature dependence. So just need to be aware of. Okay, so I'm going to exercise you guys for 5 or 10 minutes on a couple of problems. They're basically the same problem, but one is simpler and sort of semi-conceptual. The second is numerical. So maybe what I'll do here is just work through the first one in the middle above, and then have you work in groups of 2 or 3 on the second one. So here it is. This turns out to be not uncommon in practice, but I won't emphasize it too much. It's just kind of to give you a bit of understanding of how to treat capacitors that are not completely stuffed full of dielectric, or if they have dielectrics in them, it may not be just one material. And so it's the question of what happens if we have space between capacitor plates made up of more than one kind of type of material in a given part of the space. So what have we got here? A dielectric slab of thickness little d and dielectric constant kappa is inserted in the middle of a parallel plate capacitor of plate separation d. Plate area is A. What is the new capacitance? So I'm going to draw this maybe in this orientation just to save some space. So what do I have here? These things have an area A. There's an overall separation big D, and I'm going to fill this partially with a dielectric, which has a thickness little d, and also has a dielectrical constant kappa. Okay, now I put this in the middle. Fine. if I was to ask you to calculate the new capacitance of this setup, is there a sort of thing we did last session on Tuesday that might be a useful way of looking at this? I mean, there's more than one way of calculating the capacitance, but is there something we learned about with combinations of capacitors on Tuesday that might be one method of tackling this?
Could you treat it as two separate capacitors?
You want to elaborate?
So like the space in between the dielectric and one plate of the capacitor is one capacitor and the other one is another.
Okay.
Is that
I like where you're heading. In a sense, however, we can't neglect the dielectric itself, because let's say I had positive here, negative down here. I do still know that I have charges like that on the outer surface.
so would it be like three capacitors?
There you go.
Okay.
So I could treat this as three effective capacitors in series. All right. So that's one way of doing it, and actually this is what we're going to try. Again, it's not the only way. But let me, before we do this, ask you, if you're awake, the way you described it, yes, I have three capacitors in series. Here to here, from here to here, from here to here. If you were to think about the way we add capacitors in series with our reciprocal relationship, would it make any difference to the answer if I moved this around, up and down? In fact, would it make any difference if I moved it all the way to one edge? No. So in fact, we could slide this thing, and you should do this calculation to convince yourself it's true. I can slide this either to the bottom or the top and simply now treat it as two effective capacitors in series. And I'll get the same result as I would if I actually put this in the middle and treated it as three. Okay? So a little bit of a trick. And again, I'd encourage you to just play around with this to convince yourself it's true. But once you've done that, I'm going to just quickly walk you through what this looks like and treat as effectively two capacitors in series. And if that's true, I should be able to say this, that I can define the overall capacitance as the sum of the reciprocals, or the sum of the reciprocal of the overall, like this. So I've got my overall capacitance now. The reciprocal of it is the sum of the reciprocals of the individuals. So what does this look like? I claim this should look like 1. Bear with me here. This is the gap now. I've got epsilon A. And I need the gap thickness, which presumably for the gap is big D minus little d, because big D is the total space between the plates and little d is the dielectric thickness. So what's left is big D minus little d. And what I should have here is 1 over, what I'm writing here is kappa times epsilon A. And then I'm going to divide this by the thickness of the dielectric itself. Okay? And a little bit of manipulation here will tell you, in fact, that I'm going to just write this up and let you guys play around with it on your own time. If I simplify this and combine terms, it turns out that the new capacitance can be expressed in that form. Okay? So, that's one way of doing it. Of course, I can also go back to some of my earlier pieces of knowledge. For example, I can look at the calculation of potential differences as a negative of the integral of the electric field over some distance. And I can work it that way. I'm going to get the same sort of answer. So I want you to play around with this a little bit, and in particular I want you to play around with it right now in the context of this second problem. It's basically exactly this, but with some numerical features and a couple of new things that it's asking. So I want you to work with 2 or 3 people sitting next to you, and then we'll quickly go through it. I've got at least one more worked example that I'm going to post in my notes, which reminds me, I'm not sure all of you realize this, and I haven't said it for a while. Usually, when I don't get to go through all these problems in class, I make sure to post them in my notes. So if you're looking for more worked examples, some of them a little more substantial, just check back on my posted notes from class. All right, so take a look at this. Very similar setup. We've got some actual parameters now, but again, it's got a dielectric not fully filling the gap between 2 capacitor plates. And we want to figure out, in this particular setup, what are the electric fields within the gap and then within the dielectric. So see if you can make use of what we've kind of talked about so far to figure out what those electric fields are. I'm going to give you 5 or so minutes on that. So find a friend or 2 to work with. We're good? Okay, let's go. I want to hear lots of talking. Find somebody to, I can tell fairly immediately if I've given you enough to work with or not.
Like so.
If I haven't, that's okay. I want you to talk with your neighbors and kind of just bang heads on this. See what you need to know.
Because F1 that's the bridge, that's like the capacitor for the dielectric acid. So the calculated report that is take because the formula is because it's not in that formula is
Yeah. Please talk. Doesn't matter if you're not sure what you're doing. The best way to find out is to talk to somebody else who maybe also doesn't have much idea.
Right, so then we have this example, and then this we give the numbers essentially the same thing, right? Except what's different is we're finding and we have so what's different is like I think we use I think we have to find it. So it's like I think both of them are oh wait, no, it's like
If you're stuck, like, find somebody to talk
right,
to. Seriously.
we're finding like
In a minute, I'm going to write a couple of hints on here. I want you guys to work it. Same size as the plates.
oh, we have them. So we can find Q, right?
Yeah, so that's
It's like in
the same. No, that's a rectangle. that area.
So we want
The
to
plate is 20 by 28 centimeters rectangle. It's like this. That's a plate.
so that
Got it? Okay.
I guess right because find C, so find C, one circle there, and then two others. So then you how do I keep and because like we know the capacity, we know the Q1 divided that's right, so we know that dielectric is just I guess we
A couple more minutes. We'll talk it through.
I guess if so we know this. Oh, okay, yeah, that's right. We know this, but we don't know this on the dielectric. So then we would solve for. So then we would what? You would do two Gauss's laws, and then like Q here equals that. So what? You do like so you solve for that. So then use Gauss's law. You said that that is over what would it be like now? If it's over to be this oh, how would it be like? Is the flux, right?
Oh, so you know that overpays it.
We know this is from
Okay, 30 seconds.
That gives you Q on, and then you just plug it into.
Separation distance 1.6 centimeters contains a dielectric slab.
Okay, lying down, good. All right. Again, it's not the only way, but one possible way of tackling this. What do I expect just to be the electric field where there's no dielectric?